Welcome everyone. In this video lecture, we will solve a MOSFET circuit problem at DC and it is from the Microelectronics circuit book. So the question is the NMOS and PMOS transistor in the circuit shown below. So the upper one is your PMOS and NMOS based circuitry. Both are the mesh transistor with K and S W by L for NMOS and Kp dash W by L of PMOS equals to 1 milliampere volt square. So these are the things given here. Okay, I am just highlighting these are the thing given. Okay, and the value of threshold voltage is given for the NMOS 1 volt, for the PMOS minus 1 volt. By assuming channel length modulation 0, so we have to neglect channel length modulation for both devices. Find the drain current ID N and IDP, and as well as voltage V 0, as well as V 0 is the output. Okay, for three different condition, vi equals to 0 volt, vi 2.5 volt, and vi equals to minus 2.5 volt. So this one is the question. So first of all, we are assuming for the say for vi equals to 0 volt, means when we are giving a 0 volt, what should be the v naught value, what should be the idp idn, we have to find. So for this purpose I am just redoing the same circuit here. Okay, so this one is the same circuit. So here what we can do, we have to say this value vi value is 0 volt. Okay, so now this one is 0 volt. So first we have to identify the transistor PMOS, that is your PMOS and NMOS, in which state. Okay, so first we have to think about for NMOS transistor, or we can simply say the QN transistor. Okay, for the QN transistor, first it is operating or not, first we have to find. For this purpose we have to find, get VGS value. Okay, VGS for NMOS, so I am writing VGSN. So it should be our VGN minus VSN. Here it is source, this terminal is our gate in, source, drain of NMOS, so we can also write N. Okay, and this one for the drain of P, gate of P, and source of P. Source is connected to the supply. Okay, so why we are doing, because first we have to check VGS is greater than equals to VT or not, VTN. So then we can say this one is operating, it is on or off. So that's why the first thing that we have to do, we have to find the gate to source voltage. So here VGN is now 0 volt. Here it is 0 volt, so make it 0, minus V or S of N, source of N terminal is connected to minus 2. So it should be 2.5 volts simply. So 2.5 volt. So here what we have concluded, that the VGSN is greater than VTN, because this one is 1 volt. Okay, so this one is always greater. Okay, so this is in the NMOS in the on state. So I am writing here, this is in the on state. Okay, similarly we have to do the thing for the PMOS, because first we have to identify in which. Okay, so again for the PMOS, again we have to find VGS of P. Okay, so what we can write, VGP minus VSP. Okay, so VGP is always 0, because the both the gate is connected to 0 volt, so it should be 0 volt, minus VSP is connected to 2.5 volt. S is, so this one is simply 2.5 or minus 2.5. So now here what we can conclude, that VGS of P will be less than VTP. Okay, clear? This one is less than, because here this one is minus 2.5 volt, will be less than VTP. This is the condition. So this one is also the PMOS is in the on state. Okay, for this one is very crucial thing. First, in any problem we have to identify it is on or off by using this condition. So Once again, I am highlighting this one for the VI 0 volt. So what we are doing? First, we are finding this one, it is okay or not. If not, then it is in the off. So again, it is also we have to do for this one for the PMOS. So now what we observed that the both one transistor is in the on state. So this is in the on state. So here the both the transistor Qn and Qp are perfectly matched. In the question, it is given. Okay, I have to select pencil. Here Qn, that is our NMOS, and Qp both are perfectly matched transistor having K and S, having K and S W by L of N, and Kp dash W by L of P is 1 milliampere per watt square, and Vt all are given. Okay, so now we know this one is in the on state. Now the circuit is the symmetrical one. Okay, and the circuit is symmetrical. Both N and NMOS and PMOS are on, perfectly matched, and these both the transistor are on, both in the on state. Okay, what we have concluded here from both are in the on state. In addition to that, so the we are not taking any channel length modulation. So this will acts as a simple resistance less, means that this one has no finite resistance, so there will be direct current flow from this one. Okay, so the resistance is finite. Okay, no finite resistance, we can say lambda equals to 0. So this one is just like a short circuit connection. Okay, but in addition to that, we have to also find the value at which this one is on or off. Okay, so here what we have concluded that this one, this transistor. Okay, once again I am drawing the same circuit here. Okay, I am just putting the same circuit here, and what we are doing, there will be direct current. Okay, because this one is acts as a zero resistance. Here resistance, there is no resistance, r is 0, r is nearly 0. So there is a direct path of current from this into this in. So there will be no flow of current in this one. I is 0. Okay. So in this path there will be no current. I will be 0. So all current will be go like this. Okay. So we can say all the current will flow directly from this side. Okay. Because this one have a mesh transistor. Okay, so in the region, okay, and vds of n, and here I am writing vgs of n minus vt of n. So we can write vdn vgn minus vtn. So vdn is 0 and vgn is minus 2. Sorry, this one is 0 volt, huh? Okay, so this one is 0 volt, this one is minus 1 volt. So this one is always greater than greater. Okay, so 0 is greater than minus 1. So this one is in the saturation region for the NMOS, for the NMOS. Okay, similarly for the PMOS, VDS of P, first we have to write a VGS P minus VTP. So VDP, VGP minus VTP. So VDP is again 0, VGP is 0, minus of minus 1. So if it is greater than, okay, this one is the condition for the PMOS in saturation region. Okay, this one is also the condition. So both having the same condition means they are following the transistor, that following the operation of transistor having the same region, saturation region. So both are in the saturation region, and so there is a direct current flow in the, so this source to drain side, source to drain, and then like this there is no current will flow from the output node because there will be resistance less, the resistor free, there is no finite output resistance. Okay, so all current will go like this. All current will come here and like this. It will go like this. Okay, so and both the transistor will be operated in the saturation region. So and there will be no current in the this side. Okay, so in this case, when this one is also sometimes we call it short circuit power dissipation, short circuit condition. Okay, short circuit condition. Okay, so in this short circuit condition there will be direct current flow. Okay, there will be no current in this direction. Okay, in the RL side. Okay, so this should be our 0. So short circuit condition is this, indirectly the current will be from P to M. Okay, and both are in the saturation region. So we have to say the current equation IDN equals to IDP equals to what we can write, K n dash W by L of 1 VGSN minus VTN whole square. Because both are in the saturation region and same current will flow. So any one equation we can write for the drain current equation in the saturation region. So simply this one is 1 milliampere per voltage square VGS. Okay, so one more line we can minus. Okay, 1 milliampere voltage square. Get voltage is 0 minus VSN is minus 2.5. Okay, this one is minus 2.5 minus 1 whole square. So this will be 1 into 2.5, 1.5 whole square. So 1 into 1.5. Okay, better to write 1.5, 1.5, then divided by 100. And this one is in the milli. So this milli, you have to write 225, and it should be. And in addition to that, okay, there will be 2. Okay, kn dash by 2. Okay, so it should be 2 also. So 225 by 2 into 10 to the power minus 3 by 100. Okay, so if we solve this one, okay, then it will come 1.125 milliampere. Okay, we have to know this formula, k n dash by 2 in case this. So here the IDP value will be simply 1.125 milliampere, and in this case V naught will be 0 volt. Okay, so V naught will be 0 volt for case 1 when A equals to, okay, when this one is for Vi equals to 0. So this one is the first one. Okay, the first condition, when Vi equals to 0, first we have to find it is on or off. Then there will be no current because both having on state and working in the saturation region. So direct current flow from the supply to ground. So there will be no flow current in the load direction. So there will be 0 current in this one. So V naught will be simply 0 because this I is 0. So R into I equals to, so this V naught equals to RL into I. I automatically 0. So 10 into 0. So this should be 0 volt. Okay. So and both are in the saturation region. So we have to directly apply the saturation drain current saturation equation by K and dash by 2 like this, and we can solve this one. Okay. So this one is the first case. Okay. Now we have to go for the second case. Okay. Say case number B. Okay, in B what we have to take, Vi equals to 2.5 volts. So again what we can do, first draw the circuit here. Okay, I have already copied one, this one. So it should be 2.5 volt. Okay, this value is 2.5 volt. So now again we have to think in transistor is on or off. Okay, so again we have to check for the NMOS. So for the time being, for the QN transistor we have to think. Okay, it is our NMOS. Okay, so again find VGSN. Okay, so VGN minus VSN. So VGN is 2.5 volt minus this should be minus of 2.5. Okay, both will be minus minus, so it should be 5 volt. So this overall value will be 5 volt, and this VGSN will be greater than equals to VTN. So this NMOS is in the on state. Okay, every time we have to find VGSN. So now this VGSN is 5 value. Okay, after solving this one is coming. Now for the QMOS, PMOS. Okay, so write it Q. Okay, now find VGSP. So VGP minus VSP. VGP is already connected here, so 2.5 volt minus it should be VSP. The VGP is 2.5, 2.5 volt. Okay, so it should be 0 volt. So this VGP is coming our 0 volt. So now this VGSP will be what? Less than, okay. Okay, means this VGSP value is less than VTP or not. Okay, for the PMOS, what VGSP value is coming 0. Okay, and this one is minus 1. So this one is not okay. This one, the condition is okay. So this one is PMOS is in the off state. Okay, for the on state, this VGSP should follow this condition, but this one is the on state condition, on state condition for the PMOS, but this is not, this one is violating this one. So this one is PMOS is in the off state, so it is in the off state, so open circuited. Is it okay? Means for the NMOS, okay, I am highlighting this. For the NMOS it is on, for PMOS it is off, because here the VGSN is greater than equals to VTN, but this one is not okay. Okay, so this one will be violating, this assumption is wrong, means okay. So this one is the on state condition, but 0 is less than equals to minus 1, no. So this one, this means this PMOS in the off state. Okay, so this one, this block. Okay, so this one means this transistor is in the off state. Okay, this one is in the off state, and okay, this one is in the, this one is in the on state. Okay, so if we read over the circuit, this one is a very good problem. So you have to, but we have to very careful about the concept, everything. So what we have observed that there is no need of this transistor. So just remove, this one is off, so better to discard all this thing. Okay, so the circuit is somehow like this. Okay, so now from this figure, the same figure we have made like this. Okay, so now after that what we have to do, this one is the circuit. Okay, so we have to go for some more page. So now the current is flowing from like this one is IDP. So this one is some resistors in general. Okay, this one is V naught, 10 kilo ohm resistance, and some current is flowing like IDP. Okay, so this IDP can be written as, okay, but before that some current is going. So okay, IDP, better to write higher potential 0 minus V naught by RL, or 10 kilo ohm. Okay, so V naught is nothing but simply minus IDP into 10 kilo ohm. If IDP is in a milliampere, so it should be V naught equals to minus IDP into 10 times. Okay, so the V naught will be negative value. Yes or no? V naught will be some negative value because the current is flowing from this side. So this should be negative, this should be 0. So this potential will be higher than this. Okay, so this should be V naught value will be negative. Okay, so now we have to first discuss means in which region the this circuit is operating. Basically this one we have to focus about this qn transistor. So now what we have to do, simply vgsn and vdsn minus vtn. Okay, so vgsn is there, so one can also write vgs. Okay, n for the nmos, the n minus vsn vdn minus vsn minus vtn, these two cancel out. At the end we will write the equality symbol. Now vgn is, that is our this voltage is 2.5 volts, so better to write 2.5 volt. And vdn, drain of this will be some negative value, and this will be also negative value minus 1. Okay, so this value 2.5 value will be greater than this one. Okay, means vgsn. Okay, okay, oh sorry. Okay, first, sorry, there will be a small mistake. Okay, first we have to know the saturation current. For the saturation, the vds value should be greater than equals to vgs minus vtn. Okay, if n. And for the linear region, vdsn should be less than equals to vgsn minus vtn. A simple characteristics. First we have to go for the step by step. Okay, this one is vds and ids curve, and this value is vgs minus vt for the nmos. This side saturation, and this side will be linear. Okay, so now we have to find vds. So vdn minus vsn, vgn minus, sorry, vsn minus vt. So this should be cancelled out. vdn is a negative value, so bet it negative. vgn is 2.5 value minus 1, and so this will be always greater. Okay, means this should be negative and this should be 1.5 volt. So the device is in the linear region. So in this case the device is in the linear region. Okay, because this vds is greater less than equals to vgs minus vtn, so this one is the condition, linear one. Okay, so the this one is the linear region. Okay, so now we have to write the drain current equation in the linear region for the nmos transistor. So this one is very good problem. So idn in the linear region, okay, make it linear, equals to k and dash w by l, there is no need to write by 2, then vgsn minus vtn, vgs minus vt, vds minus vds square by 2. Now we are assuming that the drain to source voltage will be very less, so we are neglecting 0. Okay, 0 volt means this should be 0. We are saying this one is simply 0 because this vds is very less than very less. Okay, or and this one is a square, so it is also very less, very less. Okay, so we are just neglecting, or for a very small value that same this expression can be written as vgsn minus vtn into vd for the small value of vds. Okay, so now what we can write, okay, this one for the nmos, so better to write n n. So this one is 1 milliampere per volt square. Okay, vgn n minus vsn minus vtn, and then vdn minus vsn. Okay, we have to write full. Okay, now we have to put the value for the equation. So 1 10 to the power minus 3 we can write vgn, get value, this value is 2.5, better to write 2.5 minus of this one, so minus of this one, so 2.5. Okay, minus 1 vdn minus vsn, so minus of minus, so it should be 2.5, so directly I'm writing 2.5. So 5 minus 1, so 4 vd plus 2.5, okay, into 10 to the power minus 3. Now from this one v naught value is like minus idp into 10. So this one is nothing but simply our vd value, vd equals to v naught, this v is nothing but simply our vd, because this one is a drain in, get in, and source in. So if we put this v naught in this one, okay, so the idp after putting this one, okay, so I'm directly writing, after putting v naught value, this v naught value in this equation, so it will give the some idp, 10 times of idp. Okay, so after solving all this thing, so I am directly writing, after solving, putting v naught equals to this value, so idp will be come nearly equals to, sorry, why I am saying idp, always idn, better to say idn equals to, after solving it will come minus 40 idn plus 10, after writing this 40 idp idn, sorry, idn not idp, okay, idn, sorry, so this one 40 idn plus 10, 4 into 2.5, directly I am writing. So from there the idn value will be 10 by 41, okay, with milli, so it will come 0.244 milliampere. Now this idn is known to us, so v naught after putting this one in minus, sorry, so directly to 2.44 into 10. Okay, so after putting in this one it will come minus 2.44 volt. Okay, so here what we have concluded, that idn in this case will be 0.244 milliampere, and v naught, that is our vd, will be negative, so vd will be negative minus 2.44 volt. Okay, so this one is for the vi equals to, okay, this one is just a calculation, but some concept is also there. This for vi equals to 2.5 volt. So here the NMOS is the on, but it is operating in the linear region. So this is the condition for vi equals 2.15 volt. Similarly, if we do for the this condition 2.5 volt, our PMOS, I am not doing, PMOS will be in the linear region, and NMOS will be in the off state. So in this case also very similar thing will come, v naught will become positive, in the NMOS it is negative, and idp will become a same as that of this one, 0.244. Okay, I'm writing here idp 0.244 milliamperes. Okay, so it is very simple for this one. In this case NMOS, that is our qn on, okay, qn on qp of qn in the linear. So for all these things we can easily find the value of, okay, in the first case vi equals to 0, both in the on, both q and q on, and the value will become this. Okay, the value will become for on this one v not 0 volt, and this one vi 0 volt, and okay, now for this one this will be off, this will be on, so we have to do like this, idn. Okay, so if we find there are two condition where the v naught is unknown, that is our vd. From here we have to write this v naught, and we have to write the linear equation. Okay, or for the simplification, this one we are taking, neglecting this one to 0, and then after putting this v dot, or that is our simply our vd. Okay, in this equation, so 41 id n equals to 10. Okay, so if we solve, it will give 0.224, and then we can find the vd value 2.4. so here I have written that value. Now similarly for the other case, when we are giving the negative value minus 2.5, this idp will be same, and v naught will be not negative, it should be positive. So that we have written here. Okay, so this is all about this question. So thank you for watching this video.